Gentlemen, I just wanted to go over the last couple of problems from the note sheet here from section 2.5, which is inverse trig, or I'm sorry, not inverse trig functions, derivatives of trig functions. And you can see we've got our 6 derivatives here that we're going to be using throughout this, for the rest of the year, really. And we're going to get right after it with this one, which is example 3 here, which I think the red class got through, but the blue class did not. So if you're A6, that class, you guys already have this one finished, but the blue class didn't get this one finished yet. So if you're red class, you can fast forward to get to where we get to example 4, or you can watch it again. So blue class, we are looking at a quotient here. We have secant over the quantity 1 plus tangent, and so we're going to have to use the quotient rule. So let's get after it. So the quotient rule says f prime is going to be low, which is 1 plus the tangent, the denominator that is, times the derivative of up high. Now the derivative of the secant, come over here to the chart, and it's secant tangent. So we are going to multiply by secant of x, tangent of x. And I'd remind you guys it's important to have parentheses around that 1 plus tangent. Okay, so it's low d high, so low times the derivative of the top, minus high, which is secant of x, times the derivative of the denominator. And the denominator has a derivative of, or I'm sorry, is 1 plus tangent. Derivative of 1 is just simply 0, but the derivative of tangent is secant squared. So I'm going to go secant squared here. Draw the line, and down below, the squared denominator always must go. And for that denominator of 1 plus tangent, that quantity squared, just leave it as 1 plus tangent quantity squared. Don't think about FOILing that out. It's not worth it. However, in the numerator, we're going to go ahead and simplify just a little bit to look at this secant and the tangent being multiplied into both the 1 and the tangent. So we're going to get secant of x, tangent of x. And then we're going to add a secant of x tangent squared of x. You can see the secant tangent here gets multiplied by the tangent. You're going to get a secant tangent squared. And then we're going to subtract a secant cubed of x. Draw the line, and down below, 1 plus tangent squared. 1 plus the quantity. 1 plus tangent quantity squared goes. And I think the only thing I'd do at this point is just notice that the numerator has a common factor of secant in it. So I'd probably take that secant out and be left with a tangent plus a tangent squared minus a secant squared. And in the denom we have a 1 plus a tangent of x quantity squared. Now, there's an answer. It's perfectly acceptable. It seems to be pretty well simplified. One thing I would look at, though, is just to make sure with our Pythag identities for trig, I should maybe do this over here, 1 plus the tangent squared is equal to the secant squared. That's one of our lesser-known Pythag identities. So, for example, if we had secant squared minus tangent squared, that would be equal to 1. We don't have secant squared minus tangent squared, but we have tangent squared minus secant squared. So that being the opposite of secant squared minus tangent squared, we could replace this with a negative 1 maybe, and I guess that would be the last thing I would do, is just say secant of x, tangent of x, minus 1 all over 1 plus tangent quantity squared. And now I know some of you are thinking, oh geez, is he going to be looking for us to do that on a test, because you might not remember that. I wouldn't necessarily be looking for that on a test, particularly since nothing really happened. We didn't get to cancel anything out. The only reason I bring it up is just because, say on an AP multiple choice question, you might have this in your work, and this and that, and you know that this selection here doesn't show up as one of the choices, and then you'd have to be suspicious about what if there's some identity you're missing. So it's still important to remember all your Pythag identities. But there's example 3. So now let's move on to example 4, which again is pretty straightforward, except it's a second derivative. So the only way to get the second derivative is to get the first derivative and then take the derivative of that. So if y is tangent of x, y prime is the derivative tangent, which I think you guys know from the chart is secant squared. Now, for the derivative of secant squared, I would ask that you recognize that it's secant of x times secant of x, and we're going to treat this like a product rule. And so we're going to have f and g, where both f and g are secants. So we're going to get after this and label it as y double prime. And we're going to take the derivative of the first, and the derivative of the secant is secant tangent times the second function, which is secant of x, plus the first function, which is secant of x, times the derivative of the second function, which is the derivative of secant, which is secant tangent. So obviously we have like terms here because we've got two factors of secant, and a tangent in both. So I guess I would just clean that up and say y double prime is 2 secant squareds times a tangent. Okay, secant times secant is secant squared with a tangent in there, and then of course we've got two of the same terms. And I just call that a day. I'd wrap it up with that. Okay, but again, there's no shortcut for getting a second derivative. You have to get the first derivative and take the derivative of that. For this next one, we're looking at a differential equation. These equations that have derivatives in them, y double prime plus y equals 0, trying to show that cosine is a solution to that, and then separately trying to show that sine is a solution to that. So what we're going to need, because the equation involves a second derivative, is we're going to need to know what the second derivative of each function is. So if y is cosine of x, y prime is negative sine of x. That's from our chart. Y double prime would be the derivative of negative sine of x, which is the opposite of the derivative of sine of x, which is cosine of x. Now, that's what we're going to have if we have y equal cosine of x. So I think you can see if we have y double prime plus y equals 0, and we're checking to see if this is really true, y double prime goes in and is opposite of cosine of x, plus y, which is cosine of x. Sure enough, that equals 0. So cosine, y equals cosine, is a solution to that. Now, for our other work, I'll go to red so you can tell the difference. We're talking about y being the sine of x. So y prime is cosine of x, and y double prime, again from the chart, y double prime is the derivative of cosine, which is negative sine. And I think you can see the pattern again. When we put y double prime into the equation for y double prime plus y equals 0, we're going to get negative sine of x plus y, which is sine of x, and checking to see does that equal 0. Sure enough, it does. So the pretty straightforward problem. It's always nice when they tell you to show that something is true, because you know it's going to work out. Okay. So for this last problem, we are looking at a plane flying overhead at 3,800 feet constantly. And what's happening is there's a distance between the plane and the person on the ground, and that obviously is going to be changing as the plane gets closer. That distance is going to be a little shorter. If the plane was, say, here, the person going up to look at it, that distance is going to be shorter. But what's also changing is that angle's changing, okay? I think we may have experienced this. You probably have experienced this sometime in your life. If you're looking at a plane going overhead from a distance, for example, you have a plane coming out here and you're way down here. At a distance, this distance could be a mile away. The angle doesn't move very much for that plane to move a fairly good distance. Your angle barely changes at all, and that plane's going to move fairly far. But the closer it gets to you, the more dramatically that angle is going to change as you're looking up at it. So it's kind of an interesting problem of perspective. But in order to figure out this problem, to find out how the distance is changing with respect to the angle, we've got to come up with a relationship that relates the distance and the angle. So hopefully you can recognize that we've got a right triangle situation going on in here. And right triangles in math classes always mean either Pythag or trig. And because this is a unit on trig derivative, chances are we're going to go with trig. So I think everybody would agree that the relationship between the opposite side and the hypotenuse is given by the sine of that angle. So the sine of theta is equal to the opposite side over the hypotenuse. And that's all well and good, but we have to come back up here to our problem statement, which is the rate at which the distance s is changing with respect to theta changing. So, and this is an instantaneous moment when the angle happens to be 30 degrees. Just before that it's 29.9999 degrees, and just after it's 30.0001 degrees. So we need to really find the rate at which s is changing with respect to theta. So that would be in calculus ds d theta. This is the instantaneous rate of change of this distance as the angle changes. Well, if you think of us, the work we've done, we'd kind of say, okay, well, this is sort of like our situation where we've had, dy dx. So we're thinking, okay, s is playing the role of the y value, which is changing because x is changing, and x in this case is the angle. The angle changes and it results in a change in the distance. So that implies that we need to rearrange our equation to get s by itself. We want s as the dependent variable. It depends on what the angle is. So with a quick cross multiplication, we're going to get s equals 3800 over the sine of theta. And I think you'd realize a sine in the denom, oops, said sine and wrote sine. The sine in the denom is like having a cosecant in the numerator. And we could deal with it. We don't have to write it as 3800 cosecant theta. We could just use it this way and use, say, the quotient rule and go low d high minus high d low, draw a line down below, square denominators go. Or just do it this way. But I think we would prefer this way because it's going to be pretty clean. It's a constant times a function, so the derivative is just going to be the constant times the derivative of the function. So this is the function we need to take the derivative of. So we're going to say ds d theta is the derivative of a constant times a function is the constant times the derivative of the function. Well, the derivative of cosecant from the chart is negative cosecant theta cotangent theta. And we're particularly interested in this rate of change right at the angle when it's 30 degrees. Now this is where this is a little bit important. That our derivation of all of our trig functions, because they're based on limits, that we did when we did the limit as sine of theta over theta as theta went to 0. We used theta was in radians. So this derivation of this derivative of ds d theta would be in feet per radian. And that's important to understand that whenever you're taking the derivative of trig stuff, it's always in terms of radians, and yet the angle was given in degrees. So some of the astute members listening to this right now say, well, who cares if we put 30 degrees in here or its equivalent, which is pi over 6 radians? Who cares if we use 30 degrees or pi over 6 radians as long as we get the right cosecant and the right cotangent? Well, we don't. The cosecant of 30 degrees is exactly the same as the cosecant of pi over 6 radians, but the units are going to be different because it's going to be in the units of measure of the numerator, which is distance, which is feet, per the units of the angle, which is radians, not degrees. So we can now think about plugging this in here. So we're going to get 3800. Maybe I'll pull that negative sign through to the front. Cosecant of pi over 6. Cotangent of pi over 6. So with a little help of our 30, 60, 90, with a pi over 6 being the 30, we have 1, root 3, and 2. So the cosecant is the reciprocal of sine. The sine, of course, would be 1 over 2. So the cosecant, that's going to be 2 over 1, or just 2. And the cotangent, instead of being the opposite over the adjacent, like the tangent is, it's the adjacent over the opposite. So that's going to be root 3. So we get some pretty clean numbers here. We're going to get the rate of change, ds d theta, at the instant when theta is pi over 6, is going to be negative 3800 times the cosecant of pi over 6, which is 2, times the cotangent of pi over 6, which is root 3. And I guess the only thing I would do with that without a calculator is say that's negative 7600 root 3. But again, the units would be feet per radian. Okay? And there you go. So that's the answer, would be in feet per radians. If you wanted to get degrees, you could convert from radians to degrees by doing like, let's see, pi radians is 180 degrees. So there's a thing. Every time you deal with trig ratios, trig functions with derivatives, you got to remember they're in radians. So that's it for this. We're going to get some practice doing problems like this tomorrow in class, but now you have all the tools you need.